one more. This one is called there's more than one way to skin a cat. Perhaps you've heard that phrase. I didn't just, make that up. The early electrostatics people definitely knew that there's more than one way to skin a cat. So let's solve one more problem of a potential from a continuous charge distribution. Let's have a spherical charge distribution. Right? So a uniform sphere of charge q, okay, and radius a. Okay, so we could say right here from the origin out to some radius a, and it's a sphere, like that, full of charge q. So if we're going to do this, and the question is, yes, what is the potential at the center? Of the sphere. There's charge everywhere. One way you could do it is what we've been doing, is an integral. But this would be not a fun integral to do, because you'd have this point, and you have to think about little volumes of charge out here. Inside the sphere, if you move out, difference in radius, kind of like that, and then you'd move an angle like that, but you'd move in another angle. Sort of spherical coordinates have 3 angles to them, or 2 angles to them. You have to make a little differential volume element. You have to write it in spherical coordinates and do the integral in 3 dimensions. It's doable. There's nothing wrong with doing it that way. You can do it. And add those up and get the potential. You could definitely do that. But I want to show you another way you can get the potential, and that's from Gauss's law. Remember, Gauss's law gives us the E field, and from the E field we can get the potential. So this is sort of a sidestep if you don't want to set up the integral. And if you have something that's highly symmetric, and you've already solved the problem, say, with Gauss's law, then there's no need sometimes to have to work so hard. So let's remember what Gauss's law told us about the sphere. It told us that if we were to plot the electric field versus radius, say the magnitude of the electric field, symmetry tells us it's always going to point out or it's always going to point in. So the direction is always radial. But the magnitude, recall when we did Gauss's law, is that it went up sort of linear like that at first. And then when you got to the edge, then it acted like a point charge at the center, and it came down like that. So we have a plot like that in the Gauss's law section. In here, the actual form of it was KQR over A cubed. I think it has to be cubed, right, yeah. And this is the linear part. It's linear with R. And then on the other side, when it's coming down, then it's just like a point charge, KE, these are Coulomb's constants, KEQ over R squared, standard point charge formula. So we already have the E field. We want the total potential here. Well, we want the potential difference. Let's go back to thinking about it as a difference. So when we have our point charges, we can always assume its potential is 0 at infinity. But let's get the potential at the center by first assuming the potential equals 0 at R equals infinity. We always assume that. It's just when it gets a little more complicated than a point charge, you want to remind yourself and you want to write everything out in a little more detail. So what we want to do is get the delta V going from infinity to R, or to the point we care about, right, the center. Because we're trying to find the potential of the center. And if it's a difference, it's the final minus the initial. Okay? So if we write this delta V from infinity to 0 is what we're going to do. We're going to change the radius position from infinity, bring it to 0. Because that's going to be equal to what? It's going to be equal to the potential at 0 minus the potential at infinity. Okay? Because the difference is always final minus initial. And we've already said that this is 0. This is 0 at R equals infinity, so that'll go away. So solving this actually does give us the potential at the origin for the case that it's 0 at infinity. So we just have to write that integral. Well, delta V is minus the integral from infinity to 0 of E dot ds. All right. Well, now we have to plug in for E. We have two domains. Which one do you use? The good news is it's an integral, right? An integral is a sum, so you just break it up into two sections. So this is equal to minus the integral from infinity to A, right? We're going all the way from infinity to come up to the surface, A, that's here A, infinity to A, and there the E field is, out there, it's KQ over R squared. KE Q over R squared. And remember, it's this R hat dot ds. And then we need to do the rest of the problem, minus another integral, keep summing from A to 0. Okay, like that. So now first we went infinity to here, and now we're going from here all the way to there, where we were trying to get. And that's E dot ds. E is KEQR over A cubed. KEQR over A cubed, and also R hat dot ds. Okay. Well, one thing that'll speed us up and save me a little board is that R hat dot ds, remember that's just dr. Everything's spherically symmetric, so we can just write those as dr. R hat dot ds just picks off the changes in radius, because in this case, changes around the circle don't matter. So we've talked about that before. And now we just have to do the integrals. This we saw before, that's to the r to the minus 2, becomes r to the minus 1. You divide by the minus, it cancels that minus, and you get KEQ over r, same as when we did a point charge, from infinity to A. This one is r, so it becomes, the minus stays, it becomes minus 1/2 r squared when you just integrate r. So minus KEQ r squared, and then the 1/2 makes it a 2a cubed, evaluated from A to 0, like that. All right. And now I've run out of board, so I'm going to pull this up. And we only need about one more line. So let me see. If we keep going, then we're going to get delta V is, we decided it's V at the origin minus V at infinity, which that's nothing, so it's really just the potential at the origin. So here, this is KEQ over R. KEQ over, we plug in the A, so over A, minus KEQ over infinity, but that's of course 0. So there is the potential of the point charge if we go just to the point A. But then we have to go further. We have to keep adding to the potential. This becomes minus, and let's say we plug in 0, and what do we get? Oh, we get 0. Right, so if you plug 0 in for r squared, you get 0. And then minus, and we've already put this minus out here, so that minus gives us an A there. So that's KEQ A squared over A cubed. Boy, what a mess. Let's see. So in the end, all these, so many zeros, right? That's 0. In the end, we end up with basically the potential at the origin. We have KEQ over A here. And actually, we have minus, minus is plus, and those cancel. We have KEQ over A there. They both gave the same thing, and they're both plus, so they add. So we get 2 KEQ over A. Something's fishy here, and there it is. I know you saw it, and you were all excited, and yeah, okay, I know. 2, I missed this 2. I knew a 3 had to work its way in here somewhere. I knew there was a 3 in the answer, and a 3 does show up now because we have KEQ over A and basically a half of that, KEQ over 2A. So when we combine them, this is 2 over 2, right? So 2 plus 2 is 3, so it's 3 KEQ over 2A. And then that is the total potential at the center of the sphere.